This is an explanation of coffee roasting using carbon monoxide gas, CO gas, monitoring. In this explanation, I will explain the relationship between exhaust gas concentration and the roasting phase, and explain the actual configuration of a CO gas monitoring coffee roaster. Also, after actually roasting with a CO gas monitoring system, I will explain what kind of control is performed or how the mechanism automatically stops roasting at the desired degree of roast. Finally, I will also compare the differences with other roasting monitoring systems. In roasting coffee beans, heat is applied to the beans and roasted. Broadly speaking, there are three roasting phases: dry process, Maillard reaction, and development. CO gas concentration here. The result of measuring the CO gas concentration in the exhaust appears as a yellow graph. The CO graph is zoomed in the vertical direction. The Maillard phase starts around here. CO in exhaust from around the beginning of the Maillard phase. The concentration is increasing little by little. I think you can see from this graph that it rapidly increases when entering the latter half of development. By measuring this CO concentration, it is possible to estimate how the chemical changes in roasted beans actually occur and what phase they are in. First crack and second crack are major events as roasting progresses. In this diagram, the horizontal axis is the CO gas concentration in the exhaust for each bean. The occurrence period for first crack and second crack is shown by a horizontal line. First, let's take a look at Brazil de Terra. For the most part, it's about 6 parts per million. First crack starts at about 12 parts per million, and the first crack ends. Also, the second crack started at around 60 parts per million and has been going on for a long time. Next, let's take a look at Santos number 2. This one starts the first crack at around 8 parts per million. The first crack ends at around 25 parts per million, and the second crack starts at about 78 parts per million. It ended at around 125 parts per million. By measuring the amount of CO gas per unit of time released from beans in this way, it is possible to understand the progress of roasting in real time. There are slight variations, but since cracks are affected by the physical characteristics of beans, they accurately represent changes inside beans? I don't think so. I think the amount of CO gas is probably more accurate. This figure shows the roasting results when roasting Guatemala SHB, Santos number 2, and Mocha Sadamo and stopping roasting at 4 levels of CO gas concentration. L values are measured for each. First, it's the vertical axis, but the L value is smaller at the top. The L value indicates the reflectivity of the color on the surface of the bean, and if the L value is small, it is a dark-colored bean. It is a black bean. It's a dark roast. This large L value has a high reflectivity, so it is a relatively bright bean and light roast. If roasting is stopped at 50 parts per million, then roasting is stopped before and after light roast. When roasting is stopped at 100 parts per million, it is around medium roast as an L value around medium roast. Also, when roasting is stopped at 200 parts per million, it is slightly above medium roast. Also, when roasting is stopped at 800 parts per million, it can be roasted slightly above dark roast. In this way, the degree of roasting can be determined by deciding to stop roasting according to the CO gas concentration. However, there is a slight L value for light roasting and medium roasting. This is probably because the color of green beans is originally black or whitish, so that may directly affect the light-colored finish of light roast. The measurement here is different, but it is the result when measured using an Agtron card. I will explain the roasting machine used in the live stream on X. The roasting machine I used was Jenny Cafe. Attach a control device called a smart roaster to Jenny Cafe to monitor CO gas roasting ongoing. Everything runs automatically by unmanned operation from the start of roasting until the end of cooling. The roasting system consists of 3 elements: roasting machine, smart roaster control device, artisan logger. It consists of 3 parts. I will explain how roasting is controlled. There is a CO gas sensor on the exhaust side of the roaster. The amount of CO gas per unit time measured by this sensor is sent to the smart roaster controller. At the same time, data such as roasting temperature is also sent to the smart roaster controller. The smart roaster side has a roasting profile, and the temperature and start/stop of the roaster are operated according to that roasting profile. The roasting temperature is changed according to the roasting profile, but at that time, it is now possible to measure not only the timer but also the amount of carbon monoxide gas and change the temperature while monitoring the progress of the roasting phase based on that. Log data during roasting is sent to the artisan roaster scope and recorded. This is an overview of the CO gas monitoring roasting equipment used this time. The smart roaster controller is located at this location. The setting button is now. This is the setting dial. By turning the dial, it is possible to adjust the degree of roasting, change the profile, etc. The following is an example of roasting using this CO gas monitoring system. Here is a brief explanation of the roasting profile. It starts at 90 degrees Celsius and transitions to the next temperature stage with a timer after 4 minutes. Similarly, 185 degrees Celsius is the next after 5 minutes. 200 degrees Celsius for 2 minutes. 210 degrees Celsius for 2 minutes. 220 degrees Celsius for 2 minutes. It's been running on a timer up to this point. The dry process is up to about 210 degrees Celsius, and from here on, it will enter MyR and development. MyR before development gradually began around 200 degrees Celsius. It looks like it's going to happen. 230 degrees Celsius. This is not a timer. When CO gas exceeds 7 parts per million, this 230 degrees Celsius stage ends. Next is 240 degrees Celsius. This 240 degrees Celsius will end when CO gas exceeds 16 parts per million. The temperature is changed as the roasting progresses. After 240 degrees Celsius, it came all the way to 233 degrees Celsius. The CO gas concentration at the end of roasting is 120 parts per million here, and roasting is finished with the goal of full city roasting, and then cooling is carried out. This is an example of roasting using a CO gas monitoring system. I'll explain the differences from other roasting monitoring systems, but before that, I would like to talk about the characteristics of monitoring systems. First, roasting after the Maillard reaction. The roasting phase is easy to predict. As explained earlier, the correlation between the amount of CO gas generated from beans and changes inside the beans is very good, so it is easy to predict the roasting phase. Also, stopping roasting was explained in the table, but the reproducibility of ending roasting at the desired degree of roast is very good. Also, it is not very affected by differences in the production area or process of coffee beans. However, as a drawback, there are effects on thermal power and airflow. Also, since it is affected by CO gas generated from heat sources, there is a possibility that it will be affected if fossil fuels such as gas are used. This is a comparison with other methods. One is first crack start detection using acoustic analysis. There is a way to detect the start of the first crack and start the second half of the roasting profile at the milestone. There is a question about how stable first crack detection is. There are also beans that don't crack and beans that crack in a big way. Determining the start of a first crack may not be easy. Another method is to accurately measure the surface temperature of beans using a radiation temperature system. I wonder if this is just because the surface temperature can be accurately measured, so I can't see what's going on inside the beans. I think so. I feel that it would be a bit difficult to stop automatic roasting with either method. After all, if a person intervenes, stops applying heat, and cools, I think this kind of manual operation will inevitably become necessary. When using a CO gas monitoring system, roasting can be stopped at a stable desired degree of roast.